Hello friends, welcome to engineering tutorial. So we'll resume our discussion on thermodynamics, and so far we have discussed various theoretical concepts related to heat, temperature, temperature measurement, temperature scales, then specific heat capacity, calorimetry, and about the various concepts related to heat transfer. So, just one after this current video will be discussing numericals related to those concepts, but one video I missed, which is related to the various types of basic thermometers which are used for temperature measurement. So there will be a lot of numericals on this, so that's why I thought I should include this. I don't know, I missed this video by mistake in the theoretical discussion. So before discussing the numericals, let's cover that part also. So we'll be discussing some basic thermometer setups, which are used for temperature measurement. We have covered in detail about these things in sensors and transducers and temperature measurement sensors, but here from the point of view of the thermodynamics course and the numericals related to it, we'll be discussing this. So temperature measurement using basic thermometers. So the basic thermometers which are used for temperature measurement, they are the following four generally, and some variation of it, some modification of it. So first is gas thermometers, second liquid and glass thermometers, which is based on thermal expansion of liquids. The gas thermometer is based on the gas equation, the gas laws. Then we have the electrical resistance thermometers. It is also called as resistance temperature detector, RTD. Some variation of it which we have already discussed in sensors and transducers. If you want to see that, it is also thermistor, thermally sensitive resistor. Okay, and then we have the thermoelectric thermometer, which is the thermocouple. Okay, so we'll be discussing that. So first, the gas thermometer. It is also called as gas thermometric sensor. So basically they are the same thing, gas thermometer or gas thermometric sensor. So as I said, it is based on the ideal gas equation, the gas law. PV is equal to nRT, which is a combination of Boyle's law, Charles' law and Gay-Lussac's law combined. So here P is the pressure, V is the volume of the gas, N is the number of moles of the gas, R is the universal gas constant, and T is the temperature in Kelvin scale. So this is the relationship. PV is equal to nRT. Now there are two categories of gas thermometric sensors or gas thermometers: the constant pressure gas thermometers and the constant volume gas thermometers. The constant pressure gas thermometer has a slightly complicated design and the working is also a bit complex. So generally we will have constant volume gas thermometers because they're easier to design and calibration and everything, it is easy. So the constant volume gas thermometer, it is given by this. So constant volume means the volume remains constant. In this relationship, PV is equal to nRT. The volume is constant. Okay, so here if we take the V to the denominator side on the RHS, we'll have P is equal to nR by V into T. So here the number of moles of gas, that is constant, the universal gas constant R, that is also a constant, and the volume is also constant. So here this nR by V, we can write it as a combined constant K. So P is equal to KT, or pressure is directly proportional to temperature. So the temperature fluctuations will cause fluctuations, proportional fluctuations in pressure also, as it is directly related. So here the temperature is measured with respect to the pressure readings, the readings of pressure. So the general setup, the construction of a constant volume gas thermometer is something like this. We have the gas container chamber where the gas is used, some kind of inert gas or nitrogen is also commonly used. We have a bulb, a capillary tube, and a pressure measuring device. It can be a Bourdon tube, it can be manometer or any other pressure sensor. We have discussed a lot of pressure sensors. In sensors and transducers you can see diaphragm, membrane, a lot of pressure sensors we have used, but most commonly we have a U-tube kind of manometer or a Bourdon tube. And then we have the pointer scale arrangement or a secondary electrical transducer. It looks something like this. So we have the gas chamber where the inert gas is present, then the bulb, the capillary tube, and the pressure measurement device. It can be a Bourdon tube or it can be a manometer. So this gas chamber, this is brought in contact with the surroundings where the temperature is to be measured. So as a result of this, the pressure of this inert gas, it fluctuates with respect to the temperature as per this relationship. Okay, so the pressure reading in the Bourdon tube or the U-tube manometer, that corresponds to the surrounding temperature as per this relationship. Okay, as per this relationship. Or we can also write it as P is equal to NR by V into T. This thing, this relationship. So the pressure reading, it is directly related to the temperature. Okay, so the basic mathematical formula which is used to pinpoint the specific temperature reading, it is something like this. The specific temperature which is measured is equal to the pressure at that specific temperature, Pt. Here temperature scales also come into play. So it depends what kind of scale you are using, whether you are using Kelvin scale, whether you are using Celsius scale, Romer scale, Fahrenheit scale. So depending on that, the basic formula is this, but for interconversion, this is the formula which we can use. So you can remember this formula, which we will be using a lot in the numericals while solving the numericals. So the specific temperature reading which we get, it is equal to, for a specific scale, we have to, that is the pressure reading at that temperature, which is Pt, minus the pressure at the lower fixed point divided by the pressure at the upper fixed point minus the pressure at the lower fixed point, multiplied with the difference between the temperature readings at the upper fixed point and the lower fixed point. This. So here, to measure any temperature, first we take the pressure reading at the lower fixed point for that scale, then the upper fixed point, the lower fixed point, and the temperature readings at the upper fixed point and lower fixed point, and then we use this formula to calibrate the thermometer to give us the specific temperature. So this is the thing. For Celsius scale, it will look something like this. The temperature, specific temperature, is equal to the pressure reading which we get at the specific unknown temperature minus the pressure at 0 degrees Celsius, which is the lower fixed point for Celsius scale, then the pressure at the upper fixed point, which is 100 degrees Celsius for Celsius scale, minus the pressure reading at the lower. So P0 and P100, they are taken already, it is already predetermined. Okay, and it is used for calibrating the thermometers. Okay, it will be there in the specification sheet whenever you purchase a particular, this kind of thermometer. So this will be, already there in the specifications sheet. So what will be the pressure of this thermometer, gas thermometer, at 100 degrees Celsius? What will be the pressure of this thermometer at 0 degrees Celsius? And accordingly you will calibrate this whole thermometer as per this equation to give us the result. Okay, so always remember this. Likewise, we can do the same for Fahrenheit scale, Kelvin scale, Romer scale, like that. Okay, so this is the basic uh, operating principle of gas thermometers. Okay, so the next thermometer which we'll discuss is liquid in glass thermometer. Again, there are different modifications of it, but the basic one we'll discuss. So the liquid in glass thermometer, it is the most commonly used thermometer to measure temperature. The thermometers which we use in our homes when we put it in our armpits or in our mouth to measure temperature when we have fever, that is the liquid in glass thermometer, the mercury based thermometer. So it is based on the apparent thermal expansion of a liquid which is used, the sensing liquid, the liquid which is used here. So we have discussed the thermal expansion of liquids. So it is of two types, apparent expansion and real expansion. So the coefficient of apparent expansion, it is given by the apparent increase in volume of liquid divided by original volume into rise in temperature, delta VA by V0 into delta T, where this is the apparent increase in volume, this is the original volume, and the change in temperature. And the real expansion, same thing, in the numerator we have real increase in volume. Okay, I have made a video already on this, so I'm not going into detail about all these things. You can watch the video in the thermodynamics playlist. So the coefficient of real expansion, it is apparent expansion plus container expansion. So also we have to take into consideration the container in which the liquid is present. So the increase in volume of that container by the original volume and rise in temperature, the coefficient of thermal expansion of that container is also taken into consideration. So here the general design of this liquid in glass thermometer is something like this. We have a bulb in which the liquid, which is the sensing liquid, is used. Most commonly, mercury is used, and sometimes some red alcohol, that is also used as the sensing liquid, mercury or red colored alcohol. And there is a thin opening in the bulb which is called as bore here. Okay, it is on the inside, a thin opening which allows this liquid to rise up because of thermal expansion and go down when it contracts. Okay, so this whole setup, it is placed in contact with the point where the temperature is to be measured. So because of the increase or decrease in temperature, this sensing liquid, it undergoes thermal expansion and contraction. So it goes up and down. So this is generally a transparent glass kind of a thing. That's why it's called liquid in glass thermometer, and there is a graduated and calibrated scale. So wherever this liquid level, it points, it stops, that gives us the accurate, precise reading of temperature. Okay, so the basic mathematic formula which is used to calibrate this whole thing, it is this. Similar to the pressure thermometers, the constant volume gas thermometers, which is based on pressure. So here the main sensing parameter is level of sensing liquid. Okay, that is the main parameter which is under observation. In that case, it was pressure. here it is level of the liquid. So the calibration takes something like this. So the specific temperature reading which we get, which we'll call it as capital T, is equal to the level of the liquid at that specific temperature T minus the level of the liquid at the lower fixed point for that scale divided by the level of the liquid at the upper fixed point LUFP minus the level of the liquid at the lower fixed point, multiplied with the difference between the temperature readings, that is the temperatures at the upper fixed point and lower fixed point temperature. Okay, so let's say we consider the Celsius scale here. Okay, we take the Celsius scale for example. So here what we do, we take take the thermometer, we dip it at 0 degrees Celsius, let's say ice, and we take the level reading L0. So this is one reading which we have got. Then we dip it in boiling water, that is 100 degrees Celsius, and we take the level, the mercury level or the level of the sensing liquid at 100 degrees Celsius. So these two observations we get. Okay, then we use this formula to calibrate or to design the thermometers to give us this temperature reading as per this formula. Okay, as per this relationship. This is known, this is known, this is known, and this is also known. So this temperature reading, it is directly dependent on this LT, which we get when we take the thermometer and put it in contact with that particular unknown temperature. We get the reading as per this relation because everything else is. So this is the basic principle of liquid and glass thermometers, and be using this concept to solve a lot of numericals. That's why this formula is very important. So if you see, the general format is the same. In case of pressure gas thermometers, constant volume gas thermometers, it was PT minus P0 by P100 minus P0 into 100. Same thing. In case of level, in that we have just substituted P and we get the same thing. Here in that case the main sensing parameter was pressure. Okay, pressure of the gas. In this case it is level of the sensing liquid. So the basic format of the formula is same, just the parameter which is under observation, that is different. In that case it was pressure of the gas, in this case it is level of the sensing liquid. Everything else is the same. Okay, so this is the general operating principle of liquid and glass thermometers. Okay.